Gems, a very happy new year. The year is new and so is our enthusiasm, but the goal is same, BITSAT 2025. Welcome to the Question Bank series. With every episode of this series, we are getting 10 questions stronger for BITSAT 2025. This is Question Bank number 8, wherein we are discussing the chapter of elasticity. Previously, we have discussed from chapter 1 to 7 of your 11th standard. If you have missed out on those, do check it out once you finish with this one. The videos will be available as a question bank series in the playlist section. Okay, so you know the drill. Firstly, we discuss the previous year trends from which topic of this chapter the questions are being frequently asked for BITSAT. Okay, so let's discuss within this chapter the topics which are important. Firstly, we have Young's modulus. Most of the questions, almost all of the questions will be asked from this particular topic, okay, Young's modulus, and that to one formula which is FL by A delta L. During the A series, we made a song for that, but yeah, Young's modulus is the most important topic from this chapter, okay, and in that also strain and elongation. On that 7 questions, so half of these questions were based on finding out strain and elongations. Okay, we'll come to the questions. Then we have stress and strain curve. One question was asked on that, okay. Then we have bulk modulus, one question on that, modulus of rigidity. So simple formula based questions on bulk modulus and modulus of rigidity, eta, and some other type of question. Okay, so that was the previous year trend. Okay, so I hope you can prepare accordingly to this, and let's hop into the questions now. 1 and 2 over here, this will test your concepts. So question 1, we have a wire of certain length. Suppose it can sustain a weight of 10 kgs. Now it is cut into 2 equal pieces. So you cut it in half. Then this part of the wire, each part can handle a weight of, what is the maximum weight that this part, one single half of that wire can handle is. Now you might think and be fooled by the formula of Young's modulus that it depends on the dimensions, right? Young's modulus is given by stress by strain, right? So F by A stress and strain is delta L by L, so that goes on top. So you can write it this way, right? FL by A delta L. Remember it, we'll use it in the problems to come, okay? So you might think that Young's modulus depends on the length and area and the dimensions of your particular element, whereas the truth is it does not, okay? It is a property of the material. It only depends on the material that you are using, okay? So once you cut the wire, the material is the same, right? So Young's modulus will not change, okay? So here if this wire can sustain a load of about 10 kgs, this its half can also sustain the same amount of load, okay? There will be some certain arrangements in the extensions, okay? This two might have different extensions and rest different, okay, but the force or the weight that it can handle will not change, simply because the Young's modulus will not change, right? There will be adjustment in the elongations. This and this will have different elongations, but they will balance out the maximum stress that they can handle. That will be equal, that will be same, okay? Let's come to this one. Hooke's law is applicable for. First of all, what is Hooke's law? Hooke's law is, actually if I give you the complete statement, you'll tell it directly. Hooke's law, I'll give you the half statement, says that stress is directly proportional to strain. The complete statement is stress is directly proportional to strain within the elastic limit. Okay, so the correct option over here, it's true for elastic materials. Okay, if you see the stress strain curve, initially it is linear, then we have something like this. Okay, then the plastic region, elastic region, whatever. Okay, so within this region where stress and strain are proportional, you have the Hooke's law valid. Okay, because once you remove the stress, the strain will also come back to 0. Okay, once you within the elastic limit, if you remove the stress, the strain will also become 0. Okay, the change in dimension, it will restore to original dimension if you remove the force, whereas in these regions the thing will not come back to its original dimensions. Okay, so there is a permanent deformation, you can say, plastic region and the other regions. Okay, so Hooke's law is valid. Stress is proportional to strain only within the elastic limit. So this is valid for elastic materials that retain their shape once the stress is removed. Okay, so that is about question 1 and 2. Over to the next one. To question 3 and 4. In question 3, we are given to break a wire this much amount of stress is required. Now it's not explicitly mentioned that that is stress, but you can make out using the units, right? So sigma max is 10 to the power 6 Newton per meter square, right? Force per unit area is stress. So density is D is given 3 into 10 to the power 3. You are supposed to tell the length of the wire which breaks under its own weight. Okay, so from the maximum stress, you are supposed to tell what is the length. Okay, usually we consider the systems to be massless, right? Here we are considering the rod to have mass, and this is the density. Okay, what length of the wire will break under its own weight, right? So this is the maximum stress it can handle. So the wire will break if the maximum stress mg by a, this is the force, right? Force of its own weight, mg, right? Force due to weight is mg, or weight is basically force only, so which is mg, and we have by a, so that should equal 10 to the power 6, right? That is the maximum the wire can handle. Okay, so mg, now mass is not given, but you have density. Mass, you can write it in the form of density. So mass is density into volume, just like density is mass by volume. So density into volume is mass, right? And we have this. Okay, now volume you can write as area into length, right? So the wire is cylindrical in most cases, so this is what you call a wire, right? So the area of the base into the length, that will give you the volume, right? So this area and that area will get cancelled, so you'll be left with rho Lg. So V is AL, that A and this A gets cancelled, so we have rho Lg is 10 to the power 6. So from here you can find the maximum force that, or the stress that your wire can handle. So rho is 3 into 10 to the power 3. L is some L which we are supposed to find. G is actually 9.8, but we'll take it as 10. Okay, just for simplicity purposes, since the answer are not that close. Okay, ideally you should take it as 9.8. So L is, this is 10 to the power 4, right? So this on the left hand side, 10 to the power 4 cancel, so you will be left with 100, 10 to the power 2, and 100 by 3, simple calculation. So 100 by 3 is about 33, right, which is closer to 34. Okay, if we had taken G as 9.8, it would have been more, right? It would have been, so the value less will go over here, right? It would have been more. So 34 will be the correct one. Okay, it's more closer to 34 than 30. That also you can see. So yeah, the rest of the options are a bit further apart. Okay, so 34 will be the correct choice in this question. Let's come to this one. Here we have copper, 2 wires of copper, length in that ratio, and the radii are in that ratio. They are stretched by the same force. You're supposed to tell the ratio of the longitudinal strain to the in the two cases. Okay, so first of all, longitudinal strain, right? You have to take care in this question. If you try to solve it by yourself, you can pause the video and try to solve it. Okay, pause the video here and try to solve it. Okay, 1, 2, 3, I'm revealing the answer. It's this one. If you get this one, it is absolutely incorrect. Okay, let's see why. Okay, so here we'll see F L by A delta L. Okay, so Young's modulus will remain same, right? 2 wires of copper. So same material, same Young's modulus. Okay, so F L1, lengths are different, area will be different, radii are in the ratio, and delta L. Okay, F is L2. So Young's modulus, basically I'm writing y1 is equal to y2. Okay, and I know the force is same, so I'm not writing F1 and F2. This can cancel. Lengths are different, area is different. Agreed. Okay, and this also will be different, L1, L2. Okay, now the mistake that you might have made is to take the ratio of the areas in the lengths as it is, and you might have found L1 by L2. Okay, whereas here you are supposed to find the ratio of the strain. Please read the question carefully. Okay, so what is strain over here? Basically this quantity, right? Delta L by L, delta L by L. Okay, so you need not have the ratio of L. This is just some extra info they have provided to mislead you, rather. Okay, if you mark this option. So here it is A1 and delta L by L. So I'm taking it in the denominator. So this is strain in the first case, and we'll have A2 and delta L2 by L2 strain in the second case. So you are supposed to find the ratio of strain. Now We'll find it in the same way. In the question, we have considered it as L1 by L2, right, all the ratios. So we'll find it epsilon 1 by epsilon 2. Okay, so if you see, it's inverse relation, right? Epsilon 1 by epsilon 2 is A2 by A1. So A2 by A1, which is pi r square, right? Pi gets cancelled. This is basically proportional to the square of the radius, which is this 1:4. So that will be okay, it's R2 by R1. So 16:1. Let me check that. 16:1. Yes, it is correct. Okay, so R2 by R1, right? So inverse of this ratio, this R1 by R2, R2 by R1 is 16:1. That is correct. Okay, so option B is the correct choice, not C, because you are supposed to find the ratio of strain, okay, not the length. So that is about your question 3 and 4. Over to the next one. So question 5 and 6 over here. In question 5, we are given the plot of stress versus strain for two wires. Their Young's moduli are different, y1 and y2, for wire A and B respectively. Then you are supposed to choose the correct option. Now, it's quite simple, right? Because Young's modulus is stress by strain. Okay, you can see for the slope. Okay, it's not the perfect logic, but you can see for the slope, the higher slope will have higher Young's of modulus. So slope of A is greater, right? So A, which is y1, will be greater than y2, or the better logic would be you see for a given value of strain, okay, sorry, stress. So given value of stress, so suppose this is some psi I, okay, some value of stress we are choosing. Just draw a parallel line to the x-axis. So at this value of stress, what is the strain in A and what is the strain in B? Okay, it's, you can see this, right? So epsilon 1 and epsilon 2, I can say. Okay, so for this given value of stress, these are the strains in A and B. Now strain in B is greater than strain in A. This is obvious from the graph, right? So E2 is greater than E1. So for the same amount of stress, for the same amount of force, you can say the stress or the strain produced in second one is greater than that in the first one. Okay, or you can say for the same stress, the second one is weaker than the first one, or for the same stress, you can say y1 is greater than y2. Okay, although it does not depend on the stress, but you can see from the graph, right? For a given stress, B is the strain in B, the change in dimension in B is greater than that for A, meaning B is weaker, the Young's modulus of B is small. That is the case. So let's come to this question 6. Here we have a cube which is subjected to some compression, bulk compression. So yeah, bulk compression is happening on this cube. Okay, so if the side of the cube decreases by 2%, so the decrease in the side is 2%, or we can write it as minus 2%. So since it's decrease, the bulk strain will be. Now the formula for bulk modulus is minus P V by delta V, right? The stress by strain again, modulus, right? So stress by strain. So stress is a pressure, right? Force per unit area again, and then we have change in dimension to original dimension. Now in the bulk modulus, you are changing the volume, right? So it's delta V by V. So that V goes on top. Okay. Now this is a question of simple error analysis, right? First of all, we are supposed to find delta V by V, right? The bulk strain. Okay, this is the strain due to bulk, this bulk force, right? So now delta V, how we'll find? Because we have delta A, we can find delta V, because V is A cube. Okay, you'll know simple error analysis. This will give you 3 times delta A. Okay, the power law, right? 3 times. So the error in V, relative error in V, is 3 times the relative error in A, right? So relative error in V is 3 times the relative error in A. The power law for errors. Okay, it's true for small errors, but here we'll consider this 2%, very small. So the answer will be about 6%. Okay, so that is your answer. Let's move to the next question. Question 7 and 8 over here, the last 2 questions for the day. We are ending it early today. So question 7, here we have 3 wires A, B and C as shown. They are elongation versus load graph is shown. It's not stress versus strain. Keep that in mind. They are made of the same material, so Young's modulus is same and radii is same, so area is same basically, and they are of different lengths. It's true. Okay, you are supposed to tell the longest wire is. Okay, so we are supposed to relate. First of all, we know that y a, yb, and yc will all be equal since they are made of the same material. They are Young's modulus. It's a property of the material. The material is same. Young's modulus is same. Okay. Now the next thing is, first of all, you can see the relation. Y will be given as FL by A delta L, right? So we want to see elongation, right? Elongation, and from there we want length. So let's make elongation as the subject, the strain delta L, the elongation in the length, right? So delta L is FL upon AY. Now AY is constant if you see, right? AY is constant, and so for a given load, let's see, okay, for a given load, so I'm drawing this line. So this is for some given value of load, right? So for some given value of F, okay. So for some given value of F, so F is constant, A is constant, Y is same for all them, okay. A is same and Y is same for all of them. So you can say for a given value of load, the elongation produced is directly proportional to the length. Okay, now you can relate this question to the first question that we discussed today, right? So there also it was the same material, you just cut it into half. So there was this underlying proportionality, not maybe not the exactly same since length was also changing in that case. Okay, but let's focus on this question for now. So for a given value of F, so F constant, A and Y are same because same radii, same material. Okay, you can see that delta L, the elongation, more the elongation, will imply that the length is more. Okay, so which one has the highest elongation? So C, the elongation is highest, right? So delta L for C is highest. Okay, then we have delta LB and delta LA. Okay, so the highest one will have the highest length due to this proportionality. So you can write LC is greater than LB, although the order is not asked. LC is the longest, LC, right, which is option C. Let's come to this one. For this one I might need a little bit of space, so if you are noting this down, pause the video and you can note it down. So I'll erase it now. So question 8, we have been told that the longitudinal tension, when it's 4 newtons, the length of the string is A meters. Okay, so this is A meters, and when this is 5 newtons, the tension is 5 newtons, the length becomes B meters. Now this length is the total length, right? Because when you apply the force, you have the original length. So let's call that L. Okay, L is the original length. Okay, so in the first case, when you apply 4 newtons, you'll have L plus something delta L. Okay, so that will give you A. Okay, and here also L plus some delta L. Let's denote it differently because the extension will be different. Original length will of course be the same, right? We begin with the same length. We apply 5 newtons now. Some extension is there, surely more, right? Delta L prime. So that will give us length B. Okay, so this is the case over here. Okay, and these are your lengths that go in the formula of Young's modulus, right? FL by A delta L. Okay, here also you'll have FL by A delta L. Okay, so since the material is same string, we are applying 4 newtons and 5 newtons, you can equate their Young's modulus. Okay, so F1 is different. Is it told that the length, okay, length will be L plus this A, okay, this is delta L, this is also delta L. So here L and L prime I'm saying, right? So or L1 and L2 I can say. Okay, original length is same in both the cases. So here the length of the wire is same. Okay, let's begin with this one. So we'll equate this two. So F2 is different. F1 is 4 newtons. L, we'll keep it as L for the time being. Area, okay, area will remain the same, right? So we don't have to worry about that. Delta L1, so can we write it as that? That is what I was thinking. Or else we'll keep it as delta L1. Here we'll have 5 newtons, length maybe, and area delta L2. This will surely cancel. L will be this, right? A and B. Okay, so in this case the length, total length will be, when you apply 4 newtons, it is L plus delta A, right? So and here it will be 5B. Okay, and you can write everything in the form of, oh, this is original length, right? So that also will get cancelled. That's why I had written L. So this now you can write as delta L, you can write as delta L1, you can write as A minus L. Okay, and delta L2 you can write as B minus L. Okay, so 4B minus 4L is equal to 5A, so I'm cross multiplying, minus 5L, so bring L over here, so L will be, so this will give you the original length, right? So this will be 5A minus 4B, so this is the original length of your wire. Okay, let's denote it by 1, we'll use it somewhere. So from the length now, let us calculate the length for tension 9 newtons, right? You are supposed to find tension for, sorry, the length when the tension is 9 newtons. Okay, so again, if L by A delta L, so here we will write delta L3 under 9 newtons. Okay, this is for 4 newtons, this is 5 newtons, this is 9 newtons. Again, Young's modulus remains the same, wire is the same, only the tension we are changing, right? So you can compare this with any of these ones. Okay, so you can compare it with the, so I'll write F3. Okay, so I'll compare it with the first one. You can also do it with the second one. The thing will not change. Delta L1, right? So A and A of course gets cancelled. Original length cancels. So what will you have? F3. F3 is 9 newtons. This is 4 newtons. Delta L3, that is what we are supposed to find. Actually, we are supposed to find the total length, right? When this force is applied. So original length plus delta L3. But L we already know, right? So we'll do the task of finding this L3. Okay, we'll find this L3, and that will give us our answer. So what is delta L1? Delta L1 is A minus L, right? So A minus L. Now L, I'll write it in this form, right? Because we'll want this L3 in the form of A and B, because L is also in the form of A and B. Okay, so we'll have the answer. Okay, so here we'll have 5A minus 4B, okay, in brackets. So here 9 into A minus, so I'll directly do this, A minus, so this will become plus 4B minus 4A, right? A minus 5A, that's 4A, and this minus minus plus, and here I have 4 times delta L3. This 4 can actually get cancelled throughout. So you'll have delta L3 as 9 times B minus 9 times A is your delta L3. Okay, but this is not what you are supposed to note or report. You'll see that it does not match with any of the options, right? You are supposed to report the length when the force is 9 newtons. So this will be original length plus this extension, right? So original length is 5A minus 4B plus 9B minus 9A. Okay, so this will be plus 5B and minus 4A, right? Plus 5B minus 4A, which is option B. That is your correct choice. Okay, so that's about this question. This was a good one. I hope you were able to capture the concept. So that's about today's lecture. I hope you enjoyed it. I'll see you soon in the next video, wherein we'll be discussing question bank number 9. We'll keep the grind on. We'll bring up the strategy series and the other series for BITSAT 2025. So if you align with this vision of cracking BITSAT 2025, and if you are ready to work hard, I assure you your selection. Okay, just follow the things that we are doing over here. Just put in the work, and you'll see yourself over there. Okay, so if you align with this vision, consider subscribing. I'll see you soon in the next episode. Do check out the previous videos of question bank series if you have missed out on those. Also, you have the ACE series, which is the previous year BITSAT question series, one of its kind on on YouTube entirely. Okay, so if you want to check that out, do check it out. So that's about this video, and I'll see you soon. And till then, keep enjoying physics and all the best.